going to discuss moving from a sample to a population through something called a confidence interval. So first we'll define an interval estimate. An interval estimate is a range of values used to estimate the value of a parameter. So once we have our data for our sample, this interval is going to give us some kind of range that tells us where we think the parameter is, what's happening with the population. This may or may not actually contain the value, but it does give us a range estimate for what we think it might be. In particular, we're going to look at what's called a confidence interval. So this is a particular type of interval estimate. Before we can define a confidence interval, we have to define the confidence level. And the confidence level is the probability that the parameter is actually in our interval. Most commonly, we have a 95% confidence interval, which means there's a 95% chance that the parameter is actually in our range. And a confidence interval is just a particular kind of interval estimate that uses data from your sample and uses this confidence level. So now that we have a little bit of an idea, let's see if we can get a formula. This is our formula for a confidence interval. We have the sample mean minus the z of alpha over 2, which is going to be something that's given to us by the confidence level, and we'll talk about that in a second. Sigma is our standard deviation, and n is the sample size. So the x bar sample mean will be given to us through our sample data as well as the sample size. In order to use this particular type of confidence interval, we do need to know the population standard deviation. So it can't just be the standard deviation from the sample, but instead the entire population standard deviation. And for this, we also need that z value. So the question is, what exactly is the z value? Well, alpha is always 1 minus your confidence level. So whatever your confidence level is, we do 1 minus that. And the idea is we're trying to do this normal distribution, and we're trying to get it accurate around. And so these little shaded areas are going to be our error. They're going to be the 5%, or if we do a 95% confidence interval, this is the other 5%, something like that, the 1 minus confidence level. And so this has to be alpha over 2 since there's 2 of them. So essentially we take our confidence level, do 1 minus that, divide by 2, and then try to find the corresponding z-score. So let's do an example and see if we can figure this out. For example, we have a group of 50 women that have an average height of 67 inches, and we know our population standard deviation is 3.5, and we want to find a 95% confidence interval. So there are 4 values we need to know. X bar is the mean, which in this case, it says an average of 67. Sigma is our standard deviation, n is our sample size, and then this z value needs to come from the z table. So we start by doing 1 minus our confidence level, so 1 minus 0.95 is 0.05, and 0.05, we then need to divide that by 2 to get 0.025, and so this is the number we need to look up. So here's our z table, and we need to find 0.025 in the center. So when we do that, we can see 0.025 is exactly right here at negative 1.96. Moving back here, our z is 1.96. Our formula for confidence levels already take into account positive and negative on z-score, so we always leave it positive. We're now going to start by calculating the z of alpha over 2 times sigma over the square root of n, and this is known as the margin of error. So we have 1.96 times 3.5 over the square root of 50. which is 0.97. We then need to both add and subtract this from the mean. So we do 67 minus 0.97 and 67 plus 0.97. That gives us 66.03 and 67.97. So there's a 95% chance that the average height of women is between 66.03 and 67.97 inches. We're now going to repeat this, but this time with a 99% confidence interval. So X bar is still our average height of 67. Sigma is still 3.5. And N is still 50, but this time our Z value changes. 1 minus 0.99 is 0.01. When I divide that by 2, I get 0.005. And so this is the value I now need to look up. In my table, I now need to find 0.005, which we can see is halfway between here. So I'm halfway between 2.57 and 2.58, so we'll use 2.575. Now that we have that, we can start calculating our margin of error. We have our Z value times sigma divided by the square root of N. And when we get that, we get 1.27. So now we'll both add and subtract 1.27 from our mean. We have 65.73 is less than our population mean, which is less than 68.27. So now there's a 99% chance that our actual population mean is somewhere between 65.73 and 68.27. When we used a higher confidence level, we did get a larger interval, but it also reduces error. So there is kind of this balance here, and standard is going to be to use a 95% confidence level.